alkenes last Thursday. We're going to go into alkynes today, finish that up. We did the reductive part last Thursday. I extended the homework out to Friday. I got a few emails that students were having a hard time getting those done. So if you didn't have a chance to get the best answers you could on that, I extended that out to Friday. The next homework, which is the alkynes, is due on Monday night. So please take care of looking at that. So let's continue with alkyne reactions. And remember, one of the things we have with the alkynes is we actually have 2 pi bonds, right? So that means that we have the possibility of reacting more than once. Most of the reactions are similar to alkenes, but as we saw with the reductions, we do have some modifications and some special considerations to make. So if we looked at, we could use Lindlar's catalyst, which is a poison catalyst, to get the cis form, and then we can use dissolving metal, which is sodium in NH3, to get the trans. One other thing to point out on this is that the chapter that we're actually going over in the Soderbergh book is chapter 14. It's a little bit weak on explanation for alkene and alkyne electrophilic reactions. So I've added in Canvas some extra reading. Let me know if you need any more, or I'll see if I can add a few videos on some of the more complex mechanisms. Okay, so when we look at these, right, we have those 2 pi bonds, so we need to be thinking about that. So we did the reduction, so let's look at hydrohalogenation. We react an alkyne with HBr or HCl, one of our halogenic acids. What we'll end up with is addition of the HBr across that double bond, and we will follow Markovnikov style products. So if we look at this one, we have a terminal alkyne, so that means we have one side that's going to be is going to be more substituted than the other. With an alkyne, right, we only really can have internal and terminal, right? There's only real 2 types of alkynes. So if we had an internal, both sides would be the same. But if we have a terminal, that gives us a difference between those 2 sides. So if we the nucleophile, the pi bond, right, reacts with the electrophile, the H. That then is going to give us the more stable carbocation. And in this case, it's an alkene carbocation, a little less stable than our bromine, and come back and attack that position. And if we have excess, we can get this to occur again. So that alkene is still nucleophilic. That attacks the electrophile, the H, kicks off the bromine, and forms the most stable carbocation, which happens to be the carbocation that's next to the bromine. The reason for that is that although there is a dipole moment pulling electron density to the bromine, there's also the possibility of the bromine donating its electrons back to that carbocation. So although we have an inductive destabilization, we have a resonance stabilization. Because of this, then that means that the more stable is actually where the halide is. So that when a bromide comes in and attacks, we'll end up with both halides being added to the same side. So here's a case where inductively the bromide, it would be destabilizing, but resonance, it's stabilizing. So the resonance has a bigger impact on the stabilization. So therefore I can get the bromide added at the same position. It is possible to add one equivalent to this and end up with the intermediate. The second step is somewhat faster than the first step, so it's usually not seen. Let's put it this way, it's hard to get a good yield of the intermediate where we have one bromine attached. It's possible, but it's difficult. So what you usually see here is just an excess, and you add HBr across that double bond. Okay, questions about hydrohalogenation. So regioselectivity is just like we saw with alkenes. So in this case, we're adding the bromides across the triple bond. If we use excess, we can add 2 of those. Mechanism is similar to what we saw with alkenes. In the first addition, we are going to have the formation of the brominium ion. Okay, so that's very similar to the alkene. Then our bromide is going to have to come in and attack for the backside. So the stereochemistry will be the anti-addition. So here you can see the bromines are trans to each other across that double bond. We have excess, then that can react again. I got my red lines crossing each other. So let's do it this way. That gives us the brominium ion. Again, we'll have backside attack. to give us the tetrabromide. So again, very similar to the alkene. Again, here we can stop with the dibromide. Again, you don't see it as often, but you could do it. Again, excess would be what you'd see if you went all the way to the dibromide. If it's going to stop, they need to be explicit and say something like 1 equivalent. So 1 EQ is what you would see, or 2 equivalents. 2 equivalents would be similar to excess. Excess means you have as much as you want. 1 equivalent would mean you only have enough to react once. Okay, so if we look at acid catalyzed hydration of the alkene, here we have 2 different sets of reagents. If we have an internal, then just acid and water is usually sufficient. If you have a terminal, it needs a little bit more help. And they use a mercury salt, so mercury sulfate if you're using hydrosulfuric acid. So for the terminal, you'll see the mercury. Because of this slight difference between the two, you'll notice that a lot of the problems will use the mercury no matter which one is there. I tend not to ask questions that would make you differentiate between water and acid and water, mercury, and sulfuric acid. But it's important to know the difference because you will see some problems where they just put water and acid for internals. That will give you the product, right? For the terminals, you should add the mercury, right? So water, mercury, and sulfuric acid. So this one gets kind of complicated. Sometimes you'll see them using the mercury for everything, but there are problems where they just put the water and sulfuric acid, and it works for internals. So I won't ask you to differentiate. I'm not going to ask you to show you an internal and then give you 2 choices, one with mercury and one without. Okay. The thing to remember about this is in the top one, right, there's no regioselectivity. So if we look at an internal, both of these sides really have the same substitution pattern, right? They may have something different out here, but that would be more spatial versus electronic, right? You could have some bulky group on this side that may differentiate slightly. But as far as the electronics of these 2 groups, they're both mono-substituted positions. When we look at a terminal, now we have a difference, right? We have a hydrogen and we have the carbon. And so it's going to have a difference. So that means our regioselectivity here, right, is the Marco type selectivity. And if I can spell Marco. Okay. So we're going to add the oxygen to the side with the more substitution, the side that's not the terminal position. So let's look at the mechanism on this one because it does bring up an important new group, new process that we need to look at. Okay. And to simplify it, we're just going to use the water. The mercury can act as the electrophile and actually add across the double bond. To simplify things, we're going to just work with the acid. It does that. That kind of preemptively gets the reaction started, but it's coordinating versus forming a covalent bond. So pi bond reacts with the electrophile, water leaves. We get our electrophile at the more stable position, which is the secondary position. Then water comes in and reacts with that. We end up with this position, and then with a proton transfer. We end up with this enol form. But this enol will tautomerize to the keto form. And I'm going to draw both hydrogens on there so you can see them one. And this is the ketone form, or keto. Right. Notice that in the tautomerization, I give the equilibrium arrows and not the resonance isomerization arrows. That's because there's actually a covalent bond being broken. Notice that the oxygen, hydrogen here is actually being moved down to this carbon. Okay, so tautomerization is a reaction in itself. The reason for this is that the ketone is going to be more stable than the enol. Okay. So when we're doing this reaction, in most cases, there's only a few cases where it's not this way, the ketone is going to be a more stable form of that. So the regioselectivity follows the same thing we saw with alkenes. We end up with something that looks just like the product we would have saw with alkenes, but because of this double bond and this enol formation, we get tautomerization to the ketone. Okay, so let's look at keto-enol tautomerization. Okay, there's two basic ways to do this. We can do it with acid, which of course is the way we're doing it now, or we could do it with base. If we do it with acid catalyzed, the lone pair on the oxygen come down, kicking out the pi bond, reacts with the electrophilic hydrogen. So we've added our hydrogen there. And then we get a proton transfer. To get us to the ketone. questions about this one? Next semester, you'll also see the base promoted. So let's go ahead and go through that one. Again, starting with the enol, in this case, we have hydroxide. The hydroxide can pull the proton. So we're going from the enol here to the enolate. In chemistry, if something ends with an ATE or ITE, that usually means an oxygen negative species. So enolate. And then again, the oxygen negative come down towards the double bond, kick out, pick up a hydrogen, and form the ketone. All right. Questions about the tautomerization process? Yes. Yeah, you should know the base mechanism for the test as well. You won't see it until probably next semester when you get to ketone and aldehyde reactions. But it's important, might as well learn both of them at the same time. The difference is what you're adding first. You add the proton first in the acid, you add proton second in the base, right? So that's really different. With the acid, you're going to add the proton, and then you're going to fix your proton transfer there. Here you're doing the base subtraction, and then you're doing the proton addition to the double bond. So, but it's important to go ahead and do both of them at the same time. Okay. Right, so that's ketone enol tautomerization, which is the last step to the acid catalyzed alkyne. Okay, so we had acid catalyzed hydration of alkenes. We also had oxyboration, hydroboration oxidation with alkenes. So we are going to have hydroboration oxidation with alkynes. So let's look at that one. So again, most of the time we're going to be mimicking the two reactions. So hydro. And here again, we have two different processes. So let's go ahead and show those. So for hydroboration oxidation of alkynes, since you have two pi bonds, it turns out you could add two bromines across that at the same time. So what you're going to look for is reagents where you only have one BH. So there's several of these. Diisoamyl borane is very common. So if we had diisoamyl borane, another one, BB in H9, no, BBN9. Sorry, I've been watching a lot of Star Wars with my kids, so I got confused with BB8. BB9, N9, just again, what we have is two R groups, one boron. What that allows is that you can get, you can be very careful about how you're adding the hydrogens. So your boron hydrogen, you only have one reaction, which means you can then add one equivalent and get you a better reaction. So the subtle difference here is BH3 is not our primary reagent. Okay, we're going to use something like diisoborane, some type of 2 R's with 1 BH. Second step is going to be the same. So hydrogen peroxide and base. For the internal, we still end up with a ketone. Okay, we have two possible positions where it could react, this position and that position. And both of those would result in a ketone formation. When we have a terminal, now we can get an aldehyde. So the regioselectivity here is anti-Markovnikov. So like the alkene, we do get the anti-Markovnikov addition. You don't need to know the mechanisms, but we'll walk you through kind of the intermediate steps. Okay, so we have some type of DR group like this. I mean, 2 R's and a hydrogen like this. That then results in our boron added to the least substituted side. Hydrogen added to the other side. Then our hydrogen peroxide in base solution forms the enol, but then the enol forms the, and I should have thought about this. This is actually a base promoted tautomerization. So getting back to your question, yes, you need to know the base promoted tautomerization. Since this is actually in base, that's going to be a base promoted process. Okay, questions about this one? Usually where this gets students hung up is the fact that this can give you an aldehyde and a ketone. So don't generalize it and say that the hydroboration oxidation of alkyne always gives you an aldehyde. What I see is mistakes such as just putting an aldehyde on the end of a carbon and not paying attention to where the triple bond is. So you do need to realize that the internal and the terminal give two different types of products here. The process is the same, but because internals don't have a difference between the two sides of the alkyne, you don't see a difference and you only get the alkene. Okay. All right. So if we look at the reactions we've gone through today, well, this we went, but again, hydrogen and palladium gives you almost the same reaction as the alkene. The hydrohalogenation gives you the same regioselectivity, but the thing you have to add, right? So very similar to the alkene, but what you have to add is that both halides would actually add to the same side because of this resonance stabilization here shown by this bromine positive. When we go to halogenation, again, we get the same type of brominium intermediate, which would allow us to get a trans bromide if we had added one equivalent. When we have acid catalyzed hydration, the first product, right, this enol is just like our alkene. The difference is enols will become ketones, right? So when you're well, I guess the reason I'm walking through this is when you're looking at these, know what is the same as alkenes and then what's different, right? So that way you're not trying to learn a whole new thing. What you're doing is just adding. If it happens to be an alkyne, I get the same regioselectivity I would with an alkene, but I also get a tautomerization. Okay. And then the last one, right? Again, we're doing the same addition to the least substituted side for the borane, which gives us the same type of alcohol regioselectivity we get with an alkene, but since it's an alkyne and we have this double bond here, we get tautomerization to, in this case, the aldehyde. So one of the other things we need to look at is formation of alkynes. Yes, sir. Yeah, it's just the mechanism up here, right? We're just looking at the second version of it. So both of them are the same thing. We're going from an enol to a ketone or aldehyde, right? So it's keto enol. You could call it aldo enol, but it's the same thing. And you won't find aldol shown. So the mechanism is the same. The difference is what would be over here, right? If I put an H here, it's an aldehyde. If I have an R group there, it's a ketone, but the mechanism is the same. Okay, formation of alkynes. We didn't really go over the formation of alkenes. That's because formation of alkenes is eliminations, right? When we do an elimination reaction, so E1 and E2, we end up with an alkene. And that's the main way you form alkenes is through elimination. For formation of alkynes, we need to look at double dehydration, which is going to be a little bit different. This is one of those terms that used to be used a lot, double dehydrohalogenation, but you don't see it in books much anymore. What we need here is we're going to need to add a stronger base. So we usually add an amide. The reason we need a strong base here is not the first step. The first step would have worked with any base. The second step, though, is the one where we need a little bit more kick to the reaction. So this second elimination here with the sp2 carbon and kind of a more complex molecular orbital process with that bromide is going to need a stronger base. The other caveat with this one is if we had the terminal we need to say that we have excess, because what happens, right, is that we end up with this hydrogen. But because of the base we're using, we can pull that terminal proton off. Which gives us the base. Now, which is going to be faster reaction? An acid-base reaction or the elimination reaction of the hydrogen and the bromide? Well, acid-base reactions are usually faster because you're talking about protons by themselves leaving. So what we need to see whenever we see something like this is we actually have two steps. So the first step is going to be sodium amide. The second step is going to be some type of mild proton source. So something like that, okay? So the way you would see this reaction shown out when you have the possibility of a terminal is that you'll see that it has sodium amide, usually shown as excess, right? And then followed by some mild base. Now you don't want H2SO4, right? That'll protonate the alkyne, but you could have something like, you know, ammonium chloride. Right, so you just need a mild proton source. And that's to add the proton back to the terminal alkyne. Okay, questions about this one? Okay, the regional selectivity is a little bit in question. It usually goes internal versus external versus terminal, but it always ends up with an alkyne. You don't end up with an alene. An alene would be two double bonds next to each other. You end up with the alkyne. So once you remove one of the protons, the next proton goes to make the alkyne. You don't take a bromide from a hydrogen from one side and take a hydrogen from other side and end up with two double bonds next to each other in an alene. It turns out that alene is not stable. It's less stable than the alkyne. And so we always form the alkyne. We don't form the alene. Okay. The other thing we can do for formation of alkynes is the acetylide reaction. We can start with a terminal alkyne, add sodium amide, form the acetylide, and then have that react with an electrophilic carbon. We didn't have this option with alkenes, right? So this is something we saw with substitution reactions. We can do that in multiple steps. So we can build up an alkyne, starting with the acetylide. if you wanted to go from this to this, one of the things you'll see students do is they'll just say, well, I need 2 equivalents of sodium amide followed by 2 equivalents of the bromide, right? Okay, this doesn't work. Okay, so it's a common thing you'll see in these problems is you'll try and just do, well, I'll just do 2 equivalents of the base and then I'll add 2 equivalents of the electrophile. The reason this does not work, and this is a common mistake, is that this species is what you would have in the middle, right? You'd have this dianion. This is highly unstable, right? And although you could form it under the right conditions, most of you aren't going to be at deep sea pressures and sun type temperatures, right? So this is not something you're going to see normally. So what you want to do in this step is to just go ahead and do what I did before, add 1, right? So add one side and then add the other side. So you can form that, you just have to do it in steps. Add one side, then go ahead and add the other side. Okay, other questions? All right, so this has us through alkynes. So let's do some problems and then I'll go ahead and we'll start a little bit of radical reactions today just to get us a little bit back on track for next Tuesday. So the first set, let's look at, I'll give you the reactants and products, you give me the reagents. Okay, so let's take a little bit of time, look at these 3. Give me the best reagents for this. Okay, let's go ahead and take a look. So in the first one, this is the alkene, right? We're adding 2 bromines across it, so we'll just add the bromine. Is there anything else here that's important to show? or something you would see normally? Usually you see some type of anhydrous solvent, right? So CH2Cl2 is very common. Why? Well, when you add the bromine, right, that gives you the brominium ion. And if the solvent was water or methanol or some type of protic solvent that has lone pairs, you could actually add that in the second step instead of the bromide, right? So what this says is I have no water and I have no other nucleophiles, so I can end up with the dibromide and not the halohydrin. The next one, we're going from the alkyne to the ketone. So the question is, do we have one reagent or two reagents? Well, we have two reagents. We could use, answer A would be just hydrogen, sulfuric acid. If you put the mercury, that's fine. It's not necessary in an internal group, and that would give us a ketone. But we could also, choice B, we could have done, you know, diisoamyl borane, followed by, you know, the oxidative workup. And because this is an internal, both of those reactions would have given me the same product, which is the ketone. Okay. So there's no regioselectivity because there's no regio difference between the two sides of the alkyne. Okay. Questions about this one? In the last one, we're ending up with an aldehyde, and we're starting with a terminal. So in this case, we do need to use the borane reagent, so hydration borane, followed by an oxidative workup, right, to give the aldehyde. If we had used water, mercury, and sulfuric acid, we would have ended up with the ketone. So the regioselectivity would have been different. Okay. So this next one, I'm going to give you the starting material and the reactants. I want you to pay close attention to the stereochemistry and regiochemistry. Okay, so let's try those two. And both of these have two reactions over the arrows, one and two. going to be a little easier if I start over again down here, so we can show what's going on. So Lindlar's catalyst is a poison catalyst, but it's still a metal-based catalyst, which means that the first stereos product we get is the cis alkene. And then the second step, we're adding Br2 and methylene chloride. This is going to be an anti-addition to the alkene, right, which is going to have the bromines there. So we get a very specific product. This would have been different if we had chose a different starting material. Or, I'm sorry, different first reduction. If we had taken this same starting material and looked at something like sodium in ammonia, not sodium amide, but sodium in ammonia, right? What we'd end up with is the trans, and then when we did our bromination, then we would have ended up with this product, which if we rotate, so that it looks like the other one, you can see the difference between the two products. So some of the more advanced questions you'll get is, can you pick the reagents necessary to end up with certain stereoisomers, right? In this case, by changing the first step from hydrogen and Lindlar's catalyst to the gives the cis, but sodium ammonia gives the trans. The second stereo selectivity is going to be the same, but because I change what my starting material, my starting reduction is, I end up with two different isomers. The second one, we're adding the bromine. And here, this one, we can show it up here. So with excess, what we end up in the first step is this dibromide. And then in the second step, with the sodium amide, we're going to get reduction and a majority of the internal. So what we've done here is actually just move the alkyne over. So when you're going through these reactions, look at the learning outcomes, you'll see which ones you need to know the mechanisms, which ones you don't. But you also need to think about regioselectivity, stereoselectivity, so that you can start using these to build up reactions. And that's where we're getting to, right? We're getting to the point where you should be able to convert one molecule into another molecule. Should be able to think about synthetic strategies. So this here is what we would refer to as a synthetic strategy. I'm going from one group to another. I know I can't do that in just one step. So I have to think about, what do I do first and what do I do second to end up with the right product? Let's go ahead and start on radicals. Up to this point, we've really been looking at heterolytic processes. Right? One group got both oxygens, so here the oxygen got both of those oxygens, both of those electrons, so we end up with 2 electrons and hydrogen getting plus, right? So most of the things we've done so far have been ionic. In radical reactions, what we do is give homolytic cleavage. Okay, so we have 2 bromines here. We hit that with a little bit of light. Light energy shown by H nu. So when you see the H nu, think light. And what we use is a single barbed arrow. This indicates homolytic cleavage. And we end up with radicals. Radicals in general are pretty high energy species. They can react pretty readily with many things. They also have less control than most of our ionic reactions in most cases. So if we took something like methane and we hit it with, let's lose chlorine. This is actually an industrial process. So we take chlorine, hit that with some UV light, and we can end up with the chlorine, right? And let's look at the mechanism for that. So the first thing that happens is we get initiation. Okay, so the mechanisms for a radical reaction is going to be a little bit different. They're going to have steps. So the first step of the radical reaction is initiation. What we're initiating is the formation of the radical. Again, usually light or heat. Light is when you see light, it's kind of denoting that there's going to be a radical. There's a few other things that light can do. But at this point in your career, if you see light, it's probably giving you a hint that there's going to be a radical process. So the first step is formation of the radicals. The next step is going to be propagation. So here we take our substrate, in this case methane, we're going to react it with the chlorine radical. I don't know why I went to orange. And notice we're the first thing we end up with is not what we think of as going to be the product. We end up with the abstraction of the proton. So the first step is actually abstracting a proton. The second step of the propagation, so now we're 3 down, but the second step of the propagation is then going to be that methyl radical reacting with chlorine. Now, the way to think about this is that not all the chlorine is initiated at the same time. In fact, all I need is a little bit of the chlorine to be initiated for the propagation step to occur. You never have instantaneous reaction of every single molecule in a solution or process at one time. So you're always going to have some chlorine radicals and some chlorine left. So then we get a carbon reacting with chlorine to give me the product that I was expecting, plus the chlorine radical. Okay. One of the features of propagation is that the radical we start with should be the radical we finish with. So if we think about it, all we need is a little bit of initiation to occur, and then that initiation forms this somewhat chain reaction of the chlorine going and reacting with methane, and then the chlorine being reconstituted, right? So we have to have a stoichiometric amount of the methane and the chlorine, but really we only need a little bit of initiation to get the propagation step to occur. And then the propagation step is going to continue to occur, right? We're going to continue to use chlorine radicals to react with methane, but then the methane radical is going to react with chlorine to result in a chlorine radical, right? So we have this chain going around and around and around until we get to the last process, which is termination. What's happening in termination is two radicals reacting with each other. To terminate the radical process. Some terminations just give you the starting material over again. So we could have two chlorine radicals bump into each other and form chlorine, which goes back into the reaction. But we could also have something like a carbon and two of the methyl radicals reacting with each other to give us ethane, right? Radicals are high energy species, so terminations are any two radicals, so any two radical processes. Initiation is usually pretty straightforward. There's going to be initiation where we end up dividing some type of homolytically arranged molecule. Halides are known for this. So chlorine, bromine, iodine, you hit them with some light, you can form the radicals. Propagation is going to start with one radical, do some type of process, and then result in the same radical. So propagation is pretty straightforward. So initiation and propagation are pretty well defined. Termination is the one that is any two radicals that terminate, okay? So that could be the chlorine radical, that could be the carbon radical, that could be the methyl radical plus a chlorine radical, right? That's a termination. It makes the product I wanted, but I've stopped the radical process. Questions about this one? Radical reactions can also be pretty messy because if we think about it, if I start here with CH4, methane, and react it with Cl2 with initiator with a little bit of light, I can get this, right? But I can also get this, right? Because the chlorine up here could abstract a proton. Could it abstract a proton from this molecule versus that molecule? Yes, the protons have about the same, and again, radicals are high energy species. So this could react with this as well as it could react with that. Okay, so I can get this, right? And then I could get this, and then I could get this, right? So you have all of those as possible. Depending on how you set up this reaction, you could end up with a majority of your mono substituted, right? You can also force this with excess and time to go to that. Okay. Questions about these? Okay. When we look at stability of radicals, the first thing we need to really think about is, you know, where is the radical? Is it more like the carbocation, or is it more like the carboanion? So is it an electron-rich species, or is it an electron-poor species? Does it have a full octet? No. Right? So therefore, the radical is an electron-poor species. Okay. So it behaves more like the carbocation as far as its electronic nature than the carbanion. What that means is then the possibility of stabilization increases with the substitutions. So the tertiary radical is more stable than the secondary radical, more stable than methyl, a primary more stable than the methyl. Okay, just like with our carbocation. We can also have stabilization based on resonance, right? So if we had this species reacting with a radical we can have resonance using the homolytic versus heterolytic process. Okay, so we still have resonance contributors and again, just moving around that way. So radicals can be stabilized like carbocations by conjugation. Questions about radicals? We've got a little bit more radical reactions to do on Tuesday. I don't want to go into the other reactions until you have some time to digest the alkynes. Let's do one more set of problems and then we should be out of time. So I'll give you the starting material. And the reagent, you give me the product. Okay, let's try these two. Let's take a minute. Are these three? Okay, on the first one, okay, this is a hydroboration oxidation of alkene. Okay, so that is regioselective and stereoselective. The regioselective would be to put the OH group on the least substituted side. The stereoselective part is that the hydrogen and the borane add to the same side, which would mean that the OH and the methyl group are going to be trans to each other. So one's above the ring, one's below the ring. Okay, so it has both regio and stereoselectivity. The next one, we're doing an alkyne reacting with sodium and ammonia. So this is dissolving metal. Again, not sodium amide. There's sodium in ammonia. This is going to give us the trans alkene. I don't know why I made that curvy. The next one is actually two different reactions. The first reaction is going to be hydrogen and palladium with Lindlar's, or hydrogen and Lindlar's catalyst, which will give us the alkene. The second one is catalytic hydrogenation, which will give us the Markovnikov alcohol. Now, we couldn't do this in reverse, right? We couldn't do the acid hydrolation and then try to reduce it, because once we do the acid catalyzed hydration of an alkyne, it becomes a ketone. It's no longer an enol. It turns into a ketone, and therefore we couldn't have reduced off the double bond. So this way we could take a triple bond and turn it into an alcohol by first doing the reduction and then doing the addition. Okay. All right. You got an extension on online homework. It is through tomorrow night. So if you want to go back and take another look at that, the alkyne homework is due on Monday. I've got office hours today at 10 o'clock. So you all have a good weekend. Take care of each other.